Here we go. So I work for Rally Health. We're mostly Scala shop. I learned Scala there, been working on Scala for a little over 6 years. Our first task for me was to migrate from the Zend PHP framework onto Lift web framework. So naturally, my next project was to migrate off of the Lift web framework and onto Play. But more recently, I've helped move from Play 2.3 to Play 2.5. And surprisingly, this ended up being one of the harder migrations we've ever done, namely because of binary compatibility. We have started open sourcing a lot more of our code. You can find it at github.com/rallyhealth. So what's the Play web framework? It's a popular Scala and Java web framework maintained by Lightbend. It's modeled after some web frameworks like Ruby on Rails and Django in some ways, but it's a lot less prescriptive about your models. So it gives you controllers, templates, filters. These are all just sort of functions that produce some results. Either in a template case, it's a function from the template arguments into that resulting template. In the case of controllers, it's a function from a request header to some essentially iterative of byte chunks that come into a result. They've changed it over to Akka streams, but essentially the same thing. It looks a lot like this. You have your controller will have methods that take in some parameter from the routes file. You can decide to choose a request or not. If you do, you can make it implicit. You can also pass a body parser here, parse JSON, and that will return a 400 if the request doesn't have the appropriate headers. And if it does, it'll try to parse it as JSON, and if that works, you'll get your body will be will be a JS value. All right, so what is Dotty? You're probably familiar with this by now, but it's going to become Scala 3. It's the compiler backend for that. Its emphasis is on type safety, functional programming patterns, and sort of streamlining a lot of the common things that you would do with Scala, but making it a little easier. A lot of new features. Martin Nordesky went over enums yesterday and some other interesting things like extension methods. In the past, he's talked about implicit functions, which I'll be going into more detail today. There's a lot of other really interesting stuff you should check out. Match types are quite interesting too. Multiversal equality, these types of things. So there's also a lot of features removed. XML, a canonical example, but also generic type projections, existential types, and macros, for now at least. For this talk, I've been using version 0.10.0 RC1, which came out not too long ago. And it's supported with SBT 1.2.3 and above using a plugin. So I was inspired to work on this based on a talk that Martin Nordesky gave at Scala Days last year in Chicago and on what to leave implicit. So I highly recommend checking that out. What I wanted to explore was this idea of context. He was talking about, implicits are to represent context. So, all right, well, what is context? I kind of think of it as like you have some input, say a config file or your request headers or something that is available as input, and then anything that you can sort of derive from that you want to keep available for the lifetime of that input. So in the case of an application, if your input is a config file, well, it's the lifetime of that whole application until you shut it down or restart it with some new config. Here's some other examples I come up with. Obviously, the application config example. Request headers could be some input that you would want to keep around. Maybe you want to access something from the request at some point later, or maybe a database transaction, roles and permissions, authentication information, et cetera. So one way you can pass this context around, or really the only way, is through parameterization, and there's many different forms of parameterization. So the way that you would do it in a lot of languages out there is you would just add an extra argument to your function. So take in some argument X, and then you need the context. You would just add another argument to your list. You also get, in Scala, another argument list. You can create one to do what's called currying in the Scala's format of doing that. You can also return a function, which is essentially the same as currying, but you don't have to name the second argument. And you can also abstract over the return type. And this allows you to do a lot of interesting things with type abstractions. Another one that often really you don't hear much about is returning a module. So it's sort of capturing the argument, the first argument, and then providing a set of operations you can perform on that argument. And then here you can supply your context if you wanted. And then lastly, and probably most commonly you've seen, is taking an implicit argument list. And this is not quite currying. It looks like currying, but actually the compiler looks for the context the moment you call f. You can sort of thread context through by making the thing that calls it require an implicit context. But this can kind of bubble up. If you started with, say, a function value and you want to pass this context, well, if that function value has to take an implicit, well, then you have to make that a def instead of a val. And so this can, changing something to require an implicit argument list can propagate kind of in ways that you might not want. So what's new in Scala 3 is that you can put the implicit keyword into the function. Same as you did with returning a function in its relationship to the explicit method currying, where you don't have to name the implicit argument, and you can abstract over it in the return type. So this has a lot of interesting properties. All right, so I want to talk a little bit more about modules because I think this is kind of relevant. Everything in Scala is an object. You can think of it like that. Every object can have methods, and a module, it's kind of like an object that is created in memory, or it could be a package object, and you can invoke methods from that. The apply method is sort of a special method that allows an object to be invoked like a function. And of course, that's how function is actually implemented. It has other methods like and, then, and compose, and so forth, but the main method is apply. Returning a module is a great way to capture some of the dependencies and return a set of named functions based on those fixed dependencies. Modules that have no dependencies, you can use a singleton object pattern for that using the object keyword. Good example of when you would use modules is, say you're building a dependency injection, or you're building your system through dependency injection. You want to decouple the components from each other and instead have them depend on abstractions so that you can modify the implementations without having to recompile the things that depend on them. So here's an example of some silly web framework web application you might build. You have your services module, your collection module, and maybe your collection module depends on a database module, and you have an implementation called Postgres module. And these modules can be dependent on each other. And the constructor of user service may depend on the user collection, for example, and the user collection may depend on Postgres connection. That's sort of pattern of building everything outside of these classes is inversion of control. So for dependency injection, I highly recommend Adam Warski's talk on dependency injection. He goes over the various ways of doing it through using constructor-based dependency injection as you would sort of do in Java, and showing how this is actually, for the most part, it's what you should start with. It's really easy to do, and it scales well, and it's has a lot of benefits. But there's one reason you would want to, you might want to use a monad, and that is, or monad or a function, and that is if you want to put the argument into the context you want to take, you want to put that into the argument of the method so that each method becomes a function that you can parameterize. So this is just a visualization of the object graph. Ideally, if you're doing manual dependency injection, you want it to be acyclic. If you have a cycle and you're using manual dependency injection, you're either going to end up with an infinite loop where the thing's trying to construct, A is trying to construct B, is trying to construct C, which depends on A, and you just cycle. Or if you're eagerly evaluating, you'll get a null pointer exception. But once you have your whole application wired up, everything in your application should be configured as needed there. You can recreate some of the submodules with new inputs. Okay, so I'm moving a little fast because I realize I have less time than I thought, and I want to get to the demo, so bear with me. But we have, first example case of how we might parameterize passing this context. We could just use explicit functions. So here we're taking a function of execution context and returning a future int. Never mind the fact you probably would never need to add two integers in a future. That makes no sense. But just for demonstration purposes. So you would take your implicit execution context, call your future. That requires an implicit execution context. Great, passes it along for you. In this second method here, we're doing a little bit more with our results. So we're saying, okay, we want to take some result and report it on IoT. I actually don't know what IoT stands for, but I saw it in Adam Worski's talk, and so I figured I'd just throw it in here. Now whenever I look up IoT, I see Internet of Things, and I don't think that's what it means. But well, here we go. So it's reporting to the user or somewhere that this is the result of calculating that. All right, so now how do we use it? Let's say we wanted to capture these arguments and apply it at some point in the future. So I create this function of execution context and IoT to future int. So I need my arguments. I declare one of them as implicit, and I go through and do my flat maps over the future returned by add. And you'll notice that we have to take the argument there. We don't really care about EC. We just have to name it. We take these two arguments here. It matters because on the right-hand side we're executing or passing EC. We have to take them both here as well, and then we have to declare it as implicit here. And then we have to pass it explicitly in a lot of these places. So passing it with functions is pretty good. No external library is necessary. You can extract over the return type with an alias. But function arguments can only be declared as implicit when you're defining them, when you're passing them in. And you have to sort of explicitly thread them through the code. And every time that you call a function that returns a function, you're creating a closure. So some disadvantages. OK, so you can avoid having to pass these things explicitly by capturing the context in a reader monad. A reader monad basically is just, you can think of it like a function in which you can map and flat map over it, keeping the initial input. So this is just a very simple implementation of it. And so how would we end up using this? So we can create our type alias, which is one nice thing about having it all represented in the return type. And just to make the type inference a little easier, I created this async method. I had to keep explicitly putting the return type, so doing this helped to avoid that. And then now we can define our add method. We take an implicit execution context and return future. Sorry, I thought that was another arrow. And then down below where we're using it, you can see that, hey, great, we don't have to pass the execution context explicitly. In fact, we don't even have to declare that it depends on it because async op, the type, has sort of captured that knowledge for us. Of course, now, if we want to, this whole thing got moved into a for yield comprehension. So our future monad has to also be, it has its own for yield comprehension that we have to then get the result of. And but we can take our implicit execution context and great, now flat map for future works inside that block as well. And then when we want to call it later, we just pass our execution context and it passes it all the way through. This is a little bit annoying that we have to call, put EC here, but that's not a big deal. It's kind of nice. But we actually didn't implement everything that we did from before. We actually had the IoT part that I left out. So if we add that back in, it gets a little bit more complicated. We have to first off, our add method, in order to keep it in the same for yield comprehension, it has to take the same context as the report results one, which report result needs the IoT in addition to execution context. So you have some coupling that maybe you didn't want to have there. But for the sake of this demonstration, we can just bite the bullet there and say that's fine. And then now you get that monadic for. You can call add. And after you've calculated your result, you have to get out of the sort of future monad and get back into the reader monad. And that's where you have to call async again here and take the arguments explicitly, report the result. It looks kind of messy. Now we have a lot of explicit arguments because you can't declare a single argument or a tuple of arguments as implicit in Scala 2. So we have to make them explicit now, refer to them here, and pass it explicitly here. Again, for the async that we define, and then we have to make it implicit here. So you get to the end and, okay, maybe I used the wrong abstraction for this. So let's see what other advantages and disadvantages here. It's great that we can thread the arguments through the code. And you can use various tools to lift this abstraction into more interesting abstractions. Like you can use either T was talked about, where that's sort of, I think the model for using monads is better for other things, but for context, maybe not the greatest model for that. And if you add an argument, it can kind of ripple throughout the code. So changing what is required in your context can be kind of difficult. And there's a little bit of a performance cost with closures being created, and if you're going to use an external library, that may be another factor that is important to you if you care about that. All right, so this is probably what you're most familiar with, using implicit parameters. You take your implicits here, and they're threaded through the code for you. Of course, there's a downside. You have to repeat the name of these parameters everywhere that you want this implicit in scope. Consider that a downside, I guess. But it's similar to taking explicit functions. It's just sometimes you don't have to name them. So, or sometimes you don't have to pass them in where they're needed. Again, we have to declare these things as implicit, but we no longer have to do a lot of the sort of footwork of getting the right values into the places that are needed. So, all right, yeah. So there's a good reason why I think this was chosen for the future library. It's, it's efficient. And if you're defining all the places where you need the execution context, there's not really much of a problem with that. There's a bit of verbosity and boilerplateness when it comes to declaring that you need these implicit argument lists. But for the most part, all this gets threaded through the code efficiently, and you don't have to depend on external libraries to do it. OK, so what does implicit functions give you? So this is, in this case, we now are returning an implicit function that takes our context and produces some result. So an async context is something that takes an implicit execution context and returns a future of T. And our IoT context is something that, or our IoT function, something that takes a IoT and returns a T. So now our add just returns future of x plus y. And because we have an implicit execution context in scope, we don't have to name EC. It's assumed that that's what we're going to use it for. And when we report the results, we return an async context, IoT context of unit, and we have both the IoT and the execution context in scope. So, when we call it, we can, it works the same as the implicit parameters form. All these arguments are threaded through implicitly, but we don't have to declare their names at the top anymore. We don't have to like assign them to implicits. And I don't know if you noticed it, but I actually swapped the order of this so that one's returning async context, IoT context of unit, and the other one's returning IoT context, async context of int. Right, because we're returning the results at the end here. But it doesn't really matter because the Scala compiler still figures out that, OK, well, we have an implicit IoT and we have an implicit execution context. So that's all this thing needs down here, so we're good. And you'll notice we didn't declare any unneeded variable names anywhere. And if we wanted to add another context, it propagates throughout the code. And we'll find all the places where you don't have the implicit context and scope. So this seems like a pretty good fit. The only downside, you have to upgrade to Scala 3. I don't know how hard that'll be for anyone, but yeah. OK, so now I get to do the demo. What I wanted to focus on with the demo was to try and utilize this kind of request context idea in a play-like demo project and try to solve some common use cases like authentication of requests, maybe tracing requests between servers. So one common pattern we'll use for that is at where I work, we use correlation ID. So we log everything with this ID. And then in Splunk, we can kind of click on that ID and get all the requests that relate to that request. And actually, we can trace between servers as if they pass that correlation ID to other servers via headers. And we can also use it for logging. So maybe we want to have consistent logs with like everything from the request that we care about, maybe the user ID or the correlation ID and other things, all logged consistently. And we want to know, like, at compile time that this is safe. So, and I also want to retain some of the familiar patterns that you've seen in play. Lastly, I'll show that you can take this context idea and safely break it up into separate libraries if you can. All right, so here we go. Might be cranking my neck a little bit here. Move this to the other side. All right, so we'll start with just a simple example here of returning 200. So action builder, if you're familiar with play, this is, you're going to provide a function that returns a response, either async or sync. Turns out with implicit functions, you don't need to really have two separate methods anymore. Instead, what I do is I just have a responder of R, some return type, and a responder of future of response is easy to implement, just as a responder of response is easy to implement. And because this is an implicit function, if you want, you can declare that you need the request here explicitly, or not. You can just leave it out. Either way, it works fine. All right, so let's run this. Oops. Make sure it works. OK. So let's go to our main function where we're running it. All I'm doing right now is constructing the app. Let's see if I can. Here we go. So I'm going to demo. Let's build this request here. And we're going to import from our app. OK. Now, controllers gives us access to our example controller. And then we can return OK. And we'll call handle with our request. I've also implemented this like little dummy thing where I can force something to execute synchronously with this $sign. Don't do that, but just for example purposes. So we'll just say results. now when we run it, we should see we're getting a 200. Cool. All right, so next I want to kind of show, okay, well, what did this give us? So inside here we have access to the request in context. So we can say request.here, dot path, we'll say. And we can do this because request.here, it takes, sorry, this is a pattern that I used in a lot of companion objects. So what I did is I made it a trait where you can sort of extend this trait in your companion object, and it'll give you two things for free. The ability to say, I want this context to something, and that's an implicit function from the context to x. And then also I want the context that's at this location here. So you'll see me use here a lot, and that's what that means. So when I say request here, it's just pulling it out of implicit scope and getting the path. Pretty straightforward. All right, so next we can see the path down here. Can everyone see this all right? OK. So next we can show, all right, well, let's say we want to add authentication to this. So we'll have an authenticated request. And what we'll do is we'll actually refine our action to things that are authenticated. Actually, sorry, first things first. Let me show this part here. So, you probably won't just want a request by default. You might want something that is your own custom flavor of it. So, for example, created this request context, which extends this play request context, which gives you just the request by itself. I think it'll show that here. There. So it's just a trait that takes a single val, request. That's another feature in Scala 3. You can have trait parameters in sort of where the constructor would be. In addition, we want to extend this trace context. So here you can have the correlation ID, as I mentioned before. You want to log this with everything. And maybe we find a user ID in it or not. So this is something else we can define here. So in order to create this thing, we need to be able to refine this request context from our request. So here's an example how we do that. This context refiner.sync, all it's doing is saying, OK, well, I'm going to take some function, implicit function of A to B, and I'll define a way to refine it. The context refiner also, let me show this here. It's essentially like a function from your original context to a future of either an early response or your refined context. And so here, what we're doing is it's a convenient method for building it in which it's never going to be an early response, and it's never going to be in the future. It's just going to future.successful wrap this thing in a write. And then, it's something you can refine every time. So it's going to just build our base request context, and this gives us our correlation ID from the headers and our user ID from a header as well. This is not a good way to get the user ID, but we'll do that for now. OK, so now we've changed this dependency here. Obviously, we can print the request path, but we should also be able to print request context dot here dot correlation ID. Of course, we have to change how we build this controller. So let me go to my controller module. And now, instead of passing a regular play action builder, I'm going to pass this request context action builder. And you'll notice the way I did that is I just called refined on this play action builder. And refined is just something that says, OK, give me a refiner, and I'll give you a new action builder with that new refined type. And the refiner will either get the next thing that it needs, in this case the base context, and then call the next refiner with that to then get a future either of response or the new context C. And of course, if the first refiner fails and we get a response, an early response, we just return that. And we carry everything else along. So pretty easy to implement that. And then you get your new action builder. OK, so let's try running this. Now we should see both. Yeah, so we see both the path and the correlation ID. It's just randomly generated. But if we printed it twice, we would see it's the same value. All right, so let me go back to the example I was going to do here. So let's say we want to refine the request even further. We say we want an authenticated request. So you can have requests that are unauthenticated and they still have a correlation ID, but you might also want to have authenticated requests that have everything that an unauthenticated request has, but also an authenticated user ID. So we're going to define our handle. And yeah, so pretty easy definition. We're just going to return response of 200. And let's see. Oh, wait. We got to call this thing. So let's go to main. And we'll take this here. Call it result2. And call call authenticated here. OK, we got, oh, wait, we got a 401. What's that? Well, it looks like our authenticated context, the way that that is refined from the request context is by looking at the maybe user ID. And maybe user ID from the request context is received from the headers. And our request didn't have any user ID header in it. So we go back over to main. And let's add that header. So we just need a map. We're going to add a user ID. And we'll say the user ID is 1 for now. All right, so now let's try it. OK, cool. We got a 200. Pretty cool. All right, so we've refined our context. And we can also print our auth context here dot authenticated user ID. Nice. I'm going to skip ahead, though, because I want to get to the end of this. Likewise, we can define our own responders for stuff. So maybe you find that you just want to return a string. So we'll just have this example here where, whoops. Maybe we just want to say, if we return a string, it should just be a 200 with this in the body. Right now, you'll see that, just as you would expect, it tells you that, hey, there's no implicit argument of responder for string. So let's go ahead and define one. So what we do is we'll just put it right here. Okay. Same thing as before. Sync just assumes that we're going to return a response synchronously and that there's not really going to be an error that we need to handle. And there we go. So now we see that the error has gone away, and we should be able to call this from main. So we'll take this here. And I'm down to 1 minute, so I'm actually going to skip ahead and show one last example that I want to get to, which is demoing how we can do the logging. So, So let's say we have a logger. Let me take this in our arguments list up here. Didn't really go over this, but essentially an app logger is something that will take this context. If it's loggable as a map, then it will convert it to a map and put it into the log message in a formatted way. And of course, now when we call logger.info, it's going to look for the request context or some context that it can log, and we'll put that into the log message. What's nice about this is at compile time that this is safe. Assuming since it type checks, we'll just go ahead and say that that's good. Let me go add it to main so we can see the log message and what that looks like. Compile error. Oh yeah. Oops. We got to create a new app logger. Sample controller. Oh. No? There. Okay. Let me call it from main. Oops. And we'll run it. Okay, so you can see the log message down there has the path, the user ID, the correlation ID, all logged. All right, so yeah, you can find this on GitHub, context and Dotty. I'm going to go over some of the advantages of thread locals. I'm sure you guys are probably aware of why thread locals are a bad fit for this. Main takeaway, if you're going to add context, it might grow horizontally, and trimming down the size of what you want to pass in that context is easy to do if you have total control over it. Whereas thread locals, you're going to pull in maybe a lot more stuff than you need. And then essentially, if you want to break it into smaller components, you could have your blue library, your yellow library, your red library, and things that only depend on yellow library stuff can take a yellow context, and so on and so forth. At the end of the world, you're constructing that top one, and it is an everything below it, but it doesn't actually, the things below it that, in libraries that are published separately don't have to know about that. And that's pretty much it. Thanks. I assume no time for